Okay, question 5. These questions now start to become the same questions as were on the higher paper. And this is the similar sort of pattern that you'll see in the exams that you sit on the day. The end of the foundation paper is the start of the higher paper. So a light-dependent resistor is connected in a circuit. Draw a symbol for an LDR. So we mentioned this earlier. All resistors start looking like this. And this resistor is one that depends on light. So we draw a circle around it. We draw some light coming in. You just do 2 arrows and they have to come from that left-hand side. A student investigated the relationship between current and potential difference for an LDR. How should the student have connected the ammeter and the voltmeter in a circuit? Well, ammeters have to go in series. So these ones are correct, which means that answer can't be correct and that answer can't be correct because ammeters must be in series. And voltmeters, I'm just going to write that there. And voltmeters have to be parallel. What that means is that if this is your circuit, and let's say we're investigating a bulb, you have to put a voltmeter either side of the bulb to look at the amount of energy before and after. Whereas an ammeter has to just go in the circuit somewhere. So the voltmeter has to be parallel. So it's this one that both of them are correct. The diagram below shows a sketch graph of the student's results. The LDR was in a constant bright light. So constant means the same. This here relationship, just straight looking at it, is directly proportional. That's something that you should just be aware of on a graph. What it means is if our line goes through the origin, which is the 0, 0 point, so that's the origin of the graph, and it's a straight line, we say it's directly proportional. So as one value, so as the potential difference increases, the current would increase at the same rate. Just take those off to make it a little bit clearer. So the student concluded that the current in the LDR is inversely proportional. Inversely proportional. You need to know the shape of that graph as well. So an inversely proportional graph would look like that. So that was the potential difference. So increasing potential difference would cause the current, the current, to decrease. Explain why the student is incorrect. Well, the graph here does not show inversely proportional, so we can say the student's graph shows a directly proportional relationship. And let me just say why. Because the line of best fit travels through the origin, which we said was the 0, 0 point, and has a we could say it's a positive gradient. Yeah, let's say that it increases, goes up. So positive as it's as we increase this potential difference, the current is going up as well. And gradient meaning the slope of it. So high gradient would be a higher slope. So it travels through the origin and it has a positive gradient. So a positive slope, as in it's going up. Think about riding a bike up here. All right. If you were riding a bike up there, it would be hard, as opposed to a negative gradient, which would be like this one, where it would be nice. You could freewheel down there. So positive gradient means it's going up, negative going down. The student repeated the investigation with the LDR in a constant dark conditions. Constant again. So same, keeping it dark, and light-dependent resistance depends on light. So if the light is constantly dark, it means the resistance will be the same. So same resistance. Sketch on the diagram above a graph for the LDR in constant dark conditions. So the what we're going to see here is we're going to see another directly proportional relationship, but this one's going to be less steep. So something like this, wherever it has to go through that origin. So another directly proportional relationship, but less steep. Reason being is we're an LDR, the brighter the light, the lower the resistance. So if it's dark, there's going to be more resistance. The LDR was placed near a light source. The following results were recorded. Highlighter out, and we're going to highlight our values here. Write down the equation that links current, potential difference, and resistance. Before we do that, I want to show that there is in milliamps. If this appears on a foundation paper, then that is a bit mean, because milli is 1/1000th of an amp. So what that means is that we're going to have to do some kind of conversion. So 12.5 milli, so MA is actually far less than 1 amp. So we're going to divide that. I should have written the equal sign. We're going to convert that into amps. So we're going to divide it by 1,000. So if you've got a conversion, and you might towards the end of the paper, then you just got to show you're doing that conversion. Tell the examiner what you're doing. 12.5 divided by 1,000, because a milli is 1/1000th. Like a millimeter is 1,000th of a meter. A centimeter is 100th of a meter. 0.0125. 0.0125. Make sure that you keep that naught in there. 0.0125. It'd be very easy for people to write 0.125 and get their answer a little bit wrong. Write down the equation that links current, potential difference, and resistance. So we're going to go in the data sheet. We're going to get rid of that. So we're looking for current, potential difference, and resistance. And I've just realised that the one I rubbed out actually has current, potential difference, and resistance. So actually, that is the fine. So it's the same formula that we used in the last question, or the last time we had to get the data sheet out. So V equals I times R. Now, a bit of a tip with this. When we're asked to write down the equation, we can, that's the next question, we can just write it down in symbols like that. But if we get the case wrong, so for instance, if we use like this one here, it's got a lowercase t. If we use the wrong case, like an uppercase T instead of that, then we would lose the mark. So I would suggest that you write it in words. So use this part of it here. So potential difference is current times by resistance. Potential difference, same as voltage. That's current times by resistance. And if you want to, at this point, you can add in V equals I times R. Just to say, look, I know this in words and I know it in symbols. Calculate the resistance of the LDR. So this is where we use FIFA. So formula, V equals I times R. I input our values. For 4 marks this one, so there's going to be a lot to do. Right, so do we know the voltage? Yes, we do. We know the voltage is 5.50 volts. It was told here, the potential difference is equal to the current. Now we do know the current. The current was given here, and we've already figured that out, converted it, so it's there. So 0.0125. And we're going to multiply that by the resistance, which we don't know, because that is what we are trying to find out. Look, we're trying to find out the resistance there. So we just leave that as R. Now, we'd pick up a couple of marks already. We'd get 1 for the formula. We'd get 1 for inputting our values, which is why I always like to use FIFA. What we would have to do here, and this is tricky, and as I say, would only ever appear towards the end of a foundation paper, is we've got to rearrange our formula. But it's only going to give us the extra 2 marks. So let's do that. So what that means is we need to make R the subject. because we want to find resistance. So all you do is you do what's the inverse of what's happened to it. So it's currently been times by 0.0125, because maths can be read from left to right or right to left. It's in order of bin mass, not in order of left or right, like when we read. So we're going to divide R by 0.0125, because that is the inverse of what's happening to it. And when we do that, we are dividing and times by the same number, so we end up with 1. So we would end up with 1 times R, which is the same as just leaving R on its own. So by doing that, we have left R on its own. But we have to do the same thing on each side of the equal sign. So we have to get 5.5 and divide that by 0.0125 as well. So if we write our formula out again, we've now got 5.50 divided by, rather than divide by, I like to use the fraction function. So I use this as a divide. I'll show you why in a second. Divided by 0.0125, and that will give us R. So that is our the next F. So formula, input your values, fine tune it, and now we're going to write down our answer. So let's get our calculator, and let's put it here. So we had 5.5. Now, the fraction function is the third one down on the left. And it does that to your answer. The reason I like to do that is because if you've got a problem where you have to like time something under here, then sometimes if you use the divide function, it might give you something different. In this case, it's not really an issue, but I just like to always use the divide function. So the fraction function when I'm dividing. So 5.5, we should keep our numbers in, so it was actually 5.50 divided by 0. Let's start again. So 5.50 divided by 0.0125 gives us 440. 440 resistance for being ohms. Again, just check that. 5.50 over 0.0125 gives us 440. I've got the answer twice, so that suggests to me that it is correct. So 440 ohms. And it doesn't ask me to put in a certain number of significant figures, so I'm going to leave it as that. Okay, that is the end of that question.